All right, so this is a PowerPoint that goes through several of the examples on your notes. This section is technically not in our book. That's why your homework is a worksheet. We've done solving systems of equations in the past, but since we just finished talking about conic sections, I thought we might do a lesson on solving systems of conic sections. All right, so if you think about what we've done in the past, we had a system of linear equations, and I'm doing this sort of graphically. I'm solving this graphically. By the way, put your pencils down, and these examples I don't believe are on your notes, but I'll tell you when to pick up your pencil again. So clearly, in this case, if we look at the solution of a system of linear equations, and we just simply look for where those two lines intersect. And that one point is the solution. And so since there's one point of intersection, there's only one solution. And that solution would take the form of a coordinate, an x value, and a y value. All right, what about these? So first of all, these aren't lines anymore. That first equation, what would that one be? All right, so that's an ellipse. And what about the second equation? The second equation is clearly a hyperbola. So if we were to graph that, it looks like it's also centered at 0, 0. So an ellipse and a hyperbola could have 4 points of intersection. And so as a result, there are 4 solutions to this system of equations. All right, so let's think about, in general, if you have an ellipse and a hyperbola, those two different equations in a system, how many possible solutions or how many arrangements of solutions are possible? Well, you could have none. You could have 1. Could you have 2? Sure, could have 2. Could you have 3? Sure, you could have 3. What about 4? Yeah, we saw that in the last example. So yeah, 4 are possible. All right, what about if the intersection of a parabola and a line? Could you have none? Sure, maybe they just don't intersect. Could you have 1? Sure, absolutely. The line is tangent to that curve. Could have 2. Could you have 3? And I think you can all see that probably you would not have 3, right? Because a line, it is, straight, right? It can't cross that parabola in more than 2 places, so 3 is not possible. All right, what about an ellipse and a parabola? Could you have none? Sure. I've drawn like this. The ellipse could be totally inside the parabola and not intersecting it as well. But yeah, you could have it not there. The two graphs don't intersect. They could intersect once. They could intersect twice. They could intersect 3 times, or they can intersect 4 times. So knowing that you could have 4 or you could have less than 4 is important when you're solving these. Okay, so now let's pick up our pencil, and let's not solve these by graphing. Let's instead solve them by elimination, substitution, some sort of graphical solution. So try that now. All right, so I would take that second equation and solve it for x. And that way I can do a substitution. I can take the x out and plug the negative 2y plus 1 into the place for x. And then that quantity is squared. Now I have an equation just for y. I simplify it. Expand that binomial squared. And combine like terms. And then we have to solve this equation. So that's a quadratic. We can solve it by factoring. If it doesn't factor, then we want to use the quadratic formula. First thing we should do in either case is divide through by the greatest common factor of 4. That ends up factoring. And so we get y values of negative 3/2 and 2. So remember, if we look back at what this was, the first equation is an ellipse. The second equation is a line, so we know we could have two solutions. Well, it looks like we have two y values, but now we need to plug those in and find out what our two x values are. So we plug those into the equation up above that's solved for x. We get x equals -4 and x equals -3. So we end up with two coordinates. So indeed, this parabola and this line, the ellipse and the line cross in two places. So we have two solutions. All right, example 2. Again, try this without. How many solutions are possible here? So what's the first equation going to give us? That looks like an ellipse. And the second equation, if we kind of rearrange it, bring the y squared over, or take the x squared to the left and the 16 to the right, you could probably see that will end up being some sort of hyperbola. So we have a hyperbola and an ellipse, so we know we have a possible 4 solutions here. All right, so solve this using algebra, substitution or elimination. All right, so I took the first equation, instead of solving it for y, I left it in terms of y squared, and then I can simply take that whole y squared and replace it into the other equation. All right, now I have an equation just for x this time. So we want to simplify that. And then isolate the x squared, take the square root of both sides, so x is going to be equal to plus or minus 1. All right, but that's just half the answer, right? We need to take that and plug it in to the equation for y squared. So we find out y squared is 25, and in both cases, actually, it's 25, because whether we put a 1 or a -1 into that equation, the x value is getting squared. So regardless of whether we put 1 or -1 in, we'll end up with y equals plus or minus 5. So we end up with 4 points of intersection. So this one I actually graphed, so you can kind of see, indeed, you would get 4. Just to verify our solutions. Okay, so let's look at example 3. How many solutions are there? The first one is a sideways parabola, the second one is a line, so we will solve this. We will probably get potentially 2 solutions. You may not get 2, you might get none, 1, or 2. First thing I'm going to do is take the second equation and solve it for x. Then I'll substitute that into the x for the first equation. And now we have nothing but y's. And now we want to solve that. I expand that binomial, set everything equal to 0, factor. So I get a y value of 0 and a y value of 2. And now I just take those and plug them in to the equation solved for x up above. So I get one solution is 0, 0. Then when I put a y equals 2 into the other equation, I get a -4. So we get a -4, 2, and a 0, 0. Number 4. All right, so how many solutions do we have here? The first thing appears to be possibly an ellipse. And the second one, I'm sorry, a hyperbola. And the second one also appears to be a hyperbola. Okay, so solve that one using algebra. All right, so I'm going to take the second equation and I'm going to substitute, the first equation is already solved for y squared, so I'm going to take that and plug it into the second equation. I don't have to square anything because I'm substituting out the whole y squared. All right, simplify things. Just remember to distribute the negative, and I get something like 25 equals 7. Well, 25 does not equal 7, so clearly this is a contradiction, so we have no solutions in this case. So what I've done is I've graphed these so you can see why, what's going on here. So we have two hyperbolas. They're sort of next to each other. They go off infinity. They seem to have the same asymptote, but they will never intersect. They will never meet. So there was no solutions. All right, number 5. think about what those two things are and how many solutions we might get, and then meanwhile solve it algebraically. All right, so the first thing, actually both of them, the first one's a circle, the second one looks like an ellipse. So I'm taking the first equation and solving it for x squared, and then I'm going to substitute that into the second equation. My x squared gets placed in at the beginning there. We simplify this, combine like terms. We get 63y squared equals 0. We divide through by 63, y squared equals 0. And then we take the square root of both sides, y equals 0. All right, now we want to take that and plug it into one of the equations to solve for x. So I've plugged it into the equation where I already have it solved for x squared. X squared is 64, so x equals plus or minus 8. So I don't plug two values in because I only have one y value. So this gives me two solutions. So that one's possible. Let's graph this one and show you what that looks like. So we have a circle and an ellipse sort of tangent to each other. So we have two solutions. Okay, so your homework on this sort of, made up section is simply the worksheet that was part of your PDF. So worksheet 10-4A.